Hey guys, welcome to Safi Mixed. In this video, I will talk about differentiability of a function. So I'll begin from the definition of differentiability of a function and would then explain the related concepts through a very simple example. And regarding the definition, a function f of x is said to be differentiable at an interval a or b if the derivative of the function at a point x naught exists. That is, limit h tends to 0 if x naught plus h minus f of x naught divided by h. If this differentiation at point x naught of the variable x exists, we say that f of x is differentiable. F of x is said to be differentiable at an open interval a and b if the derivative f prime exists for every value within this interval. Similarly, f of x is said to be differentiable everywhere if the differential f prime of x naught exists everywhere for the open interval minus minus infinity to plus infinity. That is, if the derivative of the function f prime, that is, if the derivative f prime x naught of the function f of x exists for an open interval of the form this, it is said to be differentiable everywhere. And it is said to be differentiable over the open interval a or b if the derivative f prime x naught exists for every point within this open interval. Now, to understand this, I consider a function to be of the form of the modulus of x or absolute of x. Now, from the definition of absolute function, we know that the absolute of the function f of x is equal to x. That is, it is equal to positive x if x is greater than 0. Means when the value of x are positive, then the absolute of x is just equal to x. We drop the absolute from the x. And if the value of x is lesser than 0, means the value of x are negative, then absolute of x is taken to be negative under the condition that x is lesser than 0. That is, when the value of x is negative, we set the absolute equal to minus x. So with these things in mind, I can calculate the differentiation of the function for the two regions, that is for x greater than 0 and x lesser than 0, and what would be the differentiation at x equal to 0. So now I want to find the derivative at three different positions, that is x naught greater than 0, x naught lesser than 0, and x naught exactly equal to 0. So I would like to see the derivative of this function for these three different choices. That is, one for x naught greater than 0 is one region, x naught lesser than 0 is another region, x naught equal to 0 is a point, and we'll try to explain the non-differentiability of the function from this example. So first I consider this case, that is x naught greater than 0, then I can choose h such that x naught plus h also remains greater than 0. That is, I choose h very, very small such that x naught plus h is also greater than 0. And when that's the case, remember we would set x naught plus h mod equals x naught plus h. That's from the definition of modulus. So with that, I can write things here in the form f prime at x naught equals limit h tends to 0 first I put the value for x naught plus h, so that would become x naught plus h minus x naught divided by h, because fx naught plus h would be equal to x naught plus h modulus this thing. And now using the definition of modulus, x naught plus h is exactly equal to x naught plus h, and the modulus x is equal to and modulus of x naught equal to x naught. So with this definition I write limit h tends to 0 x naught plus h minus x naught divided by h. This x naught cancels with this minus x naught, and I'm left with limit h tends to 0 h divided by h, and this is obviously equal to plus 1. So that means for x naught greater than 0, the derivative of the function f of x exists, and that derivative is exactly equal to 1. Means the function absolute x is differentiable for x naught greater than 0. Now, what would be the situation when we choose this one case? For this case, we can write the conditions like this. Mod x naught would be equal to minus x naught, and I can choose h such that x naught plus h remains lesser than 0. When that's the case, then the mod of x naught plus h would also be equal to minus x naught plus h. That is, when x naught plus h is lesser than 0, this is negative, then the mod of x naught plus h is also negative. If I use these values for this condition in the definition, I would get this thing like this. X naught plus h would be equal to minus x naught plus h, so I'll write minus x naught plus h minus, and x naught would be equal to minus x naught, so I replace that with minus x naught, and then the whole divided with h. So if I multiply this x naught with this, in this they will become negative. I can write minus x naught minus h, in this minus that minus make it positive, so plus x naught divided by h. This x naught cancels with this minus x naught, and we are left with limit h tends to 0 minus h divided by h equals minus 1. So again, for x naught lesser than 0, the derivative of the function f of x exists, that is f prime of x naught exists, and that is equal to minus 1. Again, this is a constant. Mean the derivative of absolute of x for x naught lesser than 0 is a constant, however with negative sign. Now next we want to evaluate for this thing x naught equal to 0. And for that case, I would have the conditions. When x naught is equal to 0, then x naught mod is also equal to 0. That's all right. But for h, I have two different options. For example, this is the real line, and for x, in here, x naught equal to 0 happens over here. So to this side, x naught is lesser than 0, and to this side, x naught is greater than 0. Now, I can choose h from this side, or can choose h from this side. When choosing h from this side means I am approaching from the positive side towards 0. When choosing h from this side means I'm approaching from negative side towards 0. So here that will be h plus, and at this side it will be h minus. And we write h plus and h minus as h tends to 0 plus and h tends to 0 minus. those are the notations that we use in differentiation of the functions. So we have two options for h. H can be taken from the positive value of x reaching 0, or h can be taken from negative value of h reaching 0. So we have two options. H could be negative, h could be positive. For that case, when h is negative approaching from positive 0, we would have x naught plus h mod equals 0 plus h mod equals h mod, and this h mod would be equal to positive h, because h is positive, we are at that side. And when h is approaching towards 0 from negative value, what we would have x naught plus h equals 0 plus h mod equals h, and now h is negative, therefore this will be equal to minus h. So if we use these values in this equation, we get f prime of x naught equals limit h tends to 0 plus, that is, we are approaching from the positive side. Then x naught plus h for 0 plus is just h. I replace this with h. X naught is 0, so I just use this value and I'm not writing that, and we are left with h, and this is again equal to plus 1. So approaching from positive side towards 0, the derivative of x naught is plus 1. And now for minus 1, what would we have? We would have a prime of x naught, this is for plus, right? And obviously x naught is 0, so I can replace this, I can write this over here as a prime of 0 equal to this thing. Now for the negative case, I write f prime of 0 equals limit h tends to 0 from negative side. That would become, from negative side, x naught plus h is minus h. So I write minus h divided by h, and x naught is again 0, so I'm not writing that. And this leaves me with minus 1. And there is a problem. The derivative of a prime at x naught equal to 0 is plus 1 when we are approaching from positive side. That is, when h is plus, when h is positive. And f prime of 0 equals minus 1 when we are approaching towards 0 from minus side. So these two choices of h changes the value of f prime at x naught equal to 0. Well, this is the situation, because these two values simultaneously at x naught equal to 0 is not acceptable. They don't agree with each other. We say that f prime of 0 for h positive is not equal to f prime of 0 for h negative. So these two values do not agree with each other. Therefore, we say that the function f of x is not differentiable at x naught equal to 0. So if at a given point the value of a function from the left and right side of the value of h do not agree with each other, with that case, the function is not differentiable. This is an analytical check of the differentiability of a function. So this way you check the differentiability of a function by choosing h from positive side and negative side. We call this left side and right side values of h. At the end, if you haven't yet subscribed to Safi Mix, kindly support the channel by pressing the subscribe button. Also hit the like button in the video, and thanks for watching.